This video will show you how to find the shortest path from one vertex to another within a network. So we'll be using this example here, find the shortest path to get from A to Z, what's the length of this path. So the method we use to find the shortest path is called the shortest path algorithm. It follows a series of steps. Now the word algorithm just means a set of steps that you follow. The way that it's written on this page just here is out of the textbook. It's not fantastic. It uses this system of boxes and then adding weights onto the boxes. I'm going to show you a way that's a little bit easier to keep track of using a table. So the table I've set up looks like this. We've got the first column is the vertex, A, B, C, D, E, and Z. Then we've got the combined weights. So remember, weight is like time, distance, or money that's associated with each edge of the network. And then we've got the last column, where have we come from? What's the vertex we just came from? So we've got to start here at A and get down here to Z. So the first thing we do is we assign vertex A a weight of 0 because we're already there. Then we look at everywhere we could go from vertex A. So we've got either the option of going to vertex B or to vertex C. And we put the weights onto there. So to go from A to B is a weight of 6. To go from A to C is a weight of 4. And from B, we've just come from vertex A, just like with C, we've come from vertex A. Okay, then we look at which of those paths is shorter. So going to vertex C is only a weight of 4, whereas going to vertex B is a weight of 6. So we're going to go to vertex C first. That's where we're going to start. So the next thing we do is we look at everywhere that we could go from vertex C. So our possible options now, get rid of some of these lines. Our new possible options are vertex E or vertex D. So then we add on the total weights to get to those vertices along our path. So to get to vertex D would be our weight of 4 that it took to get to vertex C, plus this weight of 7. So to go to vertex D, it's a total weight of 11, and we've just come from vertex C. Vertex E, so we've got our weight going from C to E of 5, and to get to C it took us 4, that was from over here, so that's a total weight of 9. And again, we just came from vertex C. Okay, then we ask ourselves, which is shorter? And the distance to E was shorter. So far we've started at A, gone to C, and then gone to E with a total weight of 9. Then there's only one more step to go, E to Z. So we don't ever backtrack when we're trying to find the shortest path in the network. So we wouldn't look at going from, say, E back to B. So as far as we're concerned, E can only go to Z. So the E to Z is a total weight of 17 because we've got 9 plus 8, total weight of 17, and we've just come from E. Okay, so then we can disregard all the vertices we didn't actually go to, just ignore them. And we record backwards what our path was. So we ended up at Z. So I'll just do it down here. We ended up at Z. From Z, we came from E. From vertex E, we came from vertex C. And from vertex C, we came from vertex A. So let's go like this. Sorry, it's not quite the right place. And then you can just add some arrows. So we went A to C to E to Z with a total weight of 17. There's a couple of things you can do slightly different when you're finding the shortest path. A question might tell you that you must go through a certain point. So if you're doing that, just make sure you don't suggest any paths that don't go through that point. For example, if our path, now we didn't use the path point B because C was faster. If our path said you are not to go through point C, our path would have gone through B and it would have been different. On the other hand, we could also have a question which tells us you must go through a certain point. Now, if you're going to do that, you do it in 2 steps. The first thing you do is you go from your starting point to the point that you must go to, find the shortest possible path from the starting point to the point you must go through, and then find the shortest possible path from that middle point to the end point. So you could almost treat it like 2 separate networks. Okay, have some practice.